Welcome to our comprehensive exploration of measuring instruments in electrical science. Today, we'll dive into the fascinating world of electromagnetism and its crucial role in transforming physical quantities into measurable signals. Electromagnetism is the cornerstone of many measuring instruments, serving as a fundamental principle that converts electrical quantities into mechanical movements. Imagine a magic bridge that transforms invisible electrical signals into visible, measurable indicators. The core of this transformation lies in electromagnetic fields and forces, which can convert physical quantities like current or voltage into mechanical displacements that we can easily observe and measure. This remarkable principle allows us to interact with and understand electrical systems in ways that would otherwise be impossible. At the heart of electromagnetic measurement is a powerful concept. A current-carrying conductor placed in a magnetic field experiences a force. This fundamental principle is described by Ampere's law and Lorenz's force law, which reveals that the force on a conductor depends on multiple factors. The equation F equals B.Tech sin theta captures this relationship, showing how magnetic field strength, current, conductor length, and angle all interact. This elegant formula is the foundation for instruments like ammeters, voltmeters, and electrodynamometers, enabling precise electrical measurements. Electromagnetic devices come in several fascinating varieties, each with unique characteristics. Moving coil instruments use a wire coil suspended in a magnetic field, where current flow causes rotational movement proportional to the electrical quantity. Moving iron instruments employ a soft iron piece that moves within a magnetic field, creating a different measurement mechanism. Electrodynamometer-type instruments take complexity a step further, utilizing interactions between two magnetic fields, one from a moving coil and another from a fixed coil, to generate precise measurements. Each design offers unique advantages for different measurement scenarios. Indicating instruments rely on a sophisticated interplay of different types of torques to provide accurate measurements. The deflecting torque initiates movement in response to the measured quantity, directly proportional to its magnitude. The controlling torque, often provided by a spring, prevents excessive movement and ensures stability. Damping torque plays a crucial role in reducing pointer oscillations, allowing for quick and steady readings. These torques work together like a finely tuned orchestra, transforming electrical signals into precise mechanical movements that we can easily interpret. Deflecting torque is the primary driver of movement in measuring instruments. In moving coil instruments, this torque emerges from the interaction between a permanent magnet's magnetic field and a current-carrying coil, causing rotation that moves the pointer. For moving iron instruments, the deflecting torque results from magnetic fields generated by current flowing through a coil and interacting with a soft iron piece. This torque is fundamentally responsible for translating electrical quantities into visible, measurable mechanical movements, forming the core mechanism of many electrical measurement devices. Controlling torque acts as a crucial stabilizing force in measuring instruments. Typically provided by a spiral or hairspring, it counterbalances the deflecting torque, preventing the pointer from moving too far and ensuring a stable reading. This mechanism is like a gentle restraining hand, guiding the pointer to its precise position. In some specialized instruments, gravity can also serve as a controlling mechanism, using levers and pivots to return the pointer to zero when no current flows. The controlling torque ensures that each measurement is accurate, repeatable, and consistent. Damping torque is the instrument's way of achieving smooth, precise measurements. Its primary function is to prevent pointer oscillations after measurement, ensuring quick and steady readings. Two primary damping methods exist: Air friction damping, where a vane or disc moves through air resistance, and eddy current damping, which uses opposing currents in a metal disc to create a resistive force. Think of damping torque as a shock absorber for measurement instruments, quickly bringing the pointer to rest and providing clear, stable readings without unnecessary vibrations. Zero adjusting torque is a critical calibration mechanism in precision measuring instruments. This torque allows manual or automatic adjustment of the pointer to the zero position before taking measurements. It ensures that every measurement starts from a consistent, accurate reference point. By resetting the instrument to zero, we eliminate potential systematic errors and guarantee the reliability of subsequent measurements. This mechanism is like a reset button, providing a clean slate for each new measurement and maintaining the instrument's accuracy over time. Electromagnetic principles enable a wide range of measuring instruments with diverse applications. Ammeters and voltmeters use moving coil mechanisms to measure current and voltage, with deflecting torque proportional to the electrical quantity. Wattmeters measure electrical power using two coils, one for current and another for voltage. Galvanometers represent highly sensitive current detection instruments capable of measuring extremely small electrical currents. Each instrument type leverages electromagnetic principles and torque mechanisms to transform electrical signals into precise, readable measurements across various scientific and industrial domains. Moving iron instruments stand out as versatile measurement tools capable of handling both alternating and direct current measurements. Unlike their moving coil counterparts, these instruments use a soft iron piece that moves within a magnetic field, creating a unique measurement mechanism. Their robust design allows them to function effectively across various electrical environments. The iron piece's movement, influenced by magnetic fields generated by current flow, translates electrical quantities into readable pointer movements. This design offers remarkable adaptability, making moving iron instruments crucial in industrial and scientific settings where measurement reliability is paramount. The construction of moving iron instruments is a masterpiece of electromagnetic engineering. At its core, the instrument comprises several critical components working in harmony. A fixed copper wire coil generates the magnetic field, while a soft iron piece, carefully positioned within this field, provides the measurement mechanism. The scale and pointer work together to translate magnetic interactions into readable measurements. A precision spring provides controlling torque, ensuring stable readings, while a sophisticated damping mechanism prevents pointer oscillations. Each component is meticulously designed to transform electrical signals into accurate, consistent measurements. Moving iron instruments work on the principle of magnetic attraction or repulsion. When current flows through the fixed coil, it generates the magnetic field that interacts with the moving iron piece. This interaction causes the iron piece to move. The magnetic force on the moving iron is proportional to the square of the current. As the iron piece moves, it deflects the pointer, which indicates the strength of the magnetic field and is calibrated to show the current or voltage value. When current flows through the fixed coil, a magnetic field is generated. This magnetic field interacts with a moving iron piece, causing it to move. The movement of the iron piece results in the deflection of the pointer, which indicates the measured electrical quantity. To balance the deflecting torque caused by the magnetic force, a controlling torque is provided by a spring. This spring resists the motion of the moving iron piece and brings the pointer to a steady rest position when the forces are balanced. The final deflection of the pointer occurs when the deflecting torque is exactly balanced by the controlling torque. Moving iron instruments come in two types, attraction type and repulsion type. Focusing on the attraction type, These instruments operate based on the principle of magnetic attraction. When current flows through the coil, a magnetic field is generated. This magnetic field attracts a soft iron piece placed near the coil, causing it to move. The movement of the iron piece results in the deflection of the pointer, which indicates the measured electrical quantity. The deflection torque produced is proportional to the square of the current flowing through the coil, meaning that the deflection increases with the current strength. This makes the instrument's response nonlinear. The final deflection occurs when the magnetic force acting on the iron piece is balanced by the controlling force provided by a spring, ensuring accurate measurement. This slide explores the characteristics and applications of attraction-type moving iron instruments. These instruments operate based on the principle of magnetic attraction. Due to the nonlinear relationship between current and magnetic force, the scale of these instruments is nonlinear. This inherent nonlinearity limits their precision, making them less suitable for applications demanding high accuracy. However, they find widespread use in ammeters and voltmeters where approximate readings are sufficient. In repulsion-type moving iron instruments, a current flowing through a coil generates a magnetic field. This magnetic field repels a movable iron piece, causing it to move. The movement of the iron piece is proportional to the magnitude of the current flowing through the coil. However, the relationship between current and the force acting on the iron piece is nonlinear. This means that the scale of the instrument is not linear, which can affect the accuracy of measurements, especially for precise readings. Repulsion-type moving iron instruments are more sensitive than attraction-type instruments, making them suitable for measuring smaller currents. However, like attraction-type instruments, they also exhibit a nonlinear scale. This means that the deflection of the instrument is not directly proportional to the current, which can affect the accuracy of measurements, especially for precise readings. Repulsion-type instruments are often used in AC ammeters or voltmeters, where a slight variation in current can cause a significant enough movement for measurement. Moving iron instruments offer several advantages, including their robustness, versatility, low cost, and durability. They are suitable for industrial environments and can measure both AC and DC currents and voltages. However, they also have some disadvantages, such as their nonlinear scale, which limits their precision, and their lower sensitivity compared to other types of instruments. Additionally, the magnetic field produced in moving iron instruments can cause distortion of the measured AC signal due to harmonics, especially at higher frequencies. Moving iron instruments are versatile tools used in various applications where high accuracy is not the primary concern. They are known for their robustness, cost-effectiveness, and suitability for general-purpose measurements. Ammeters use these instruments to measure current, especially in low-cost or general-purpose applications. Voltmeters, on the other hand, utilize them to measure voltage, both in DC and AC circuits. In simpler circuits, they can even be used to measure power. Additionally, their simple operation makes them suitable for use in protection devices like circuit breakers to monitor excessive current flow, ensuring the safety of electrical systems. Moving coil instruments with permanent magnets represent a pinnacle of electrical measurement precision. Imagine a sophisticated device where a uniform magnetic field created by a horseshoe-shaped permanent magnet interacts with a delicate copper coil. When electric current flows through this coil, it experiences a magnetic force that causes rotation, with the pointer's movement directly proportional to the current's magnitude. This design offers remarkable accuracy, creating a linear scale that makes measurements incredibly reliable. These instruments shine brightest in direct current measurements, providing a clear, precise window into electrical systems' behavior. The construction of moving coil instruments is a masterpiece of electromagnetic engineering. At its core, a strong permanent magnet creates a uniform magnetic field, with carefully designed pole pieces forming a precise magnetic gap. A thin copper wire coil, mounted on a delicate pivot, sits suspended within this magnetic environment. A spiral spring provides a critical controlling mechanism, ensuring the pointer returns to zero when no current flows. The calibrated scale translates the coil's movement into readable electrical measurements. A sophisticated damping system, typically using air resistance or eddy currents, prevents pointer oscillations, guaranteeing smooth, stable readings. The working principle of moving coil instruments is a beautiful demonstration of electromagnetic interaction. When electric current flows through the suspended coil within a permanent magnet's magnetic field, it experiences the Lorentz force, a magnetic force that generates a torque causing the coil to rotate. Think of it as a precise dance between electricity and magnetism, where current strength directly influences the pointer's movement. A restoring force from the spring ensures the pointer stabilizes at a position precisely reflecting the current's magnitude. This elegant mechanism transforms invisible electrical signals into visible, measurable movements. Permanent magnet-type moving coil instruments are precision measurement devices that excel in direct current applications. A powerful permanent magnet generates a uniform magnetic field, within which a movable coil can rotate freely. When current passes through this coil, it interacts with the magnetic field, creating a torque that moves the pointer across a calibrated scale. The brilliance of this design lies in its linear relationship between current and pointer movement. Each increment of current produces a proportional deflection. This makes these instruments supremely accurate for DC measurements, serving as reliable sentinels in electrical systems. Permanent magnet moving coil instruments are renowned for their linear scale, which ensures accurate and easy-to-read measurements. They are highly sensitive to direct current, making them ideal for precise measurements in various applications. Their simple construction and low power consumption contribute to their reliability and durability. Permanent magnet moving coil instruments are widely used in precision DC measurements. They excel as ammeters and voltmeters, providing accurate readings in circuits requiring high sensitivity. These instruments are indispensable tools for scientists, engineers, and technicians in research laboratories, electronic design, and quality control. Like any sophisticated measurement tool, permanent magnet-type instruments balance remarkable strengths with inherent limitations. Their advantages include exceptional accuracy, incredibly low power consumption, and a wonderfully simple construction that enhances reliability. However, they're primarily limited to DC measurements and can be vulnerable to external magnetic field interference. This vulnerability means they require careful handling and controlled environments. Understanding these characteristics helps engineers and researchers select the most appropriate measurement tool, balancing the instrument's incredible precision against its specific operational constraints. Dynamometer-type instruments represent a significant leap in measurement flexibility, bridging the gap between AC and DC current measurements. Unlike their permanent magnet counterparts, these instruments employ two coils, a fixed and a moving coil, placed within a uniform magnetic field. When current flows through these coils, their magnetic interactions generate a torque that moves the pointer. This ingenious design allows measurements across alternating and direct current systems, offering unprecedented versatility. By transforming electrical signals into mechanical movements, dynamometer instruments provide a comprehensive view of electrical system behavior. Dynamometer-type instruments shine through their remarkable versatility and precision. Their defining feature is the ability to measure both AC and DC currents seamlessly, a capability absent in many other instrument types. The two-coil system enables complex current conversion, generating accurate readings across diverse electrical environments. Their high accuracy and linear scale make them invaluable in scientific and industrial applications. The interaction between fixed and moving coils creates a sophisticated measurement mechanism that transcends traditional instrument limitations, offering researchers and engineers a powerful tool for understanding electrical systems. Dynamometer-type instruments find critical applications across various electrical domains. They excel as wattmeters, directly measuring real power in both AC and DC circuits, a capability that makes them indispensable in power consumption monitoring. Industrial laboratories, research facilities, and electrical engineering environments rely on these instruments for precise power measurements. From monitoring complex electrical systems to analyzing power consumption in sophisticated equipment, dynamometer instruments provide comprehensive insights. Their ability to handle multiple current types makes them versatile tools in understanding electrical system performance and efficiency. Dynamometer-type instruments offer versatility, measuring both AC and DC currents. They provide accurate and reliable readings across different power ranges, making them ideal for industrial applications. While dynamometer-type instruments are highly capable, their complex design can increase manufacturing costs and maintenance requirements. Additionally, they may exhibit slight nonlinearity at higher power levels. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.